Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IISc. Today's talk is by Dr. Harshan Jagadeesh, and he'll be speaking on logging the air, strategies and performance bounds for low-latency provenance recovery and wireless networks. Dr. Harshan Jagadeesh is an assistant professor in the Department of Electrical Engineering, IIT Delhi. Prior to joining IIT Delhi, he worked as a researcher in the cybersecurity group at Advanced Digital Sciences Center, Singapore. Before that, he worked as a research fellow in the Division of Mathematical Sciences, NTU, Singapore, and in the Department of Electrical and Computer Systems Engineering at Monash University, Australia. He obtained a PhD degree from the Department of Electrical Communication Engineering, IISc Bangalore. His research interests are in the broad areas of security, wireless networks, and applications of information theory and coding theory to communication and storage. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Harshan or type them in the chat box and we'll moderate it with him. Over to you, Dr. Harshan.
Thank you, Nisha. Let me just try to switch on the camera. Okay, yeah, thanks for the introduction, and thank you everyone for attending this talk. So this talk is going to be on securing next generation wireless networks. The specific topic is what you see in the title here, logging in the air and strategies and performance bounds. So this is a joint work with some of my students at IIT Delhi. So just to take a step back and look at security. Often we hear news and read news articles about security breaches on databases or cyber-physical systems or smart grids and so on, right? So as per the root cause analysis, the main causes is the attackers would have exploited the vulnerabilities in some of these systems in terms of network architecture, whatever it is, and then they would have executed these threats to come in this news. Right? So therefore, it is imperative for all of us to secure these type of networks going forward. Now, next generation networks, as we already know, it's not just going to be communication between a mobile phone and a base station or between a laptop and a Wi-Fi router. It's going to be more complex. Examples include we're going to have vehicular networks, UAVs, there are urban transportation systems, high-speed rails, high-speed metros, industrial IoTs, and critical infrastructure. For example, it could be smart grid systems or water treatment plants and so on and so forth. Right? So in order to secure these next generation networks, there are opportunities to look at the security aspects from a fundamental viewpoint. And there is, we need to design these network systems in an untrusted environment. And the opportunities include, we have to incorporate, we have to model the cyber physical constraints and human factors into the picture. We need to develop new tools for resilience evaluation. We need to evaluate the legacy systems first, and then there are opportunities to implement or design and develop protocol stack with secure for control systems. And overall, there is scope for developing new technologies in this space, especially if you want to look at handling the security issues from first principles. Right? So among many applications that we have visited, in this particular talk, I'm going to be interested in a specific use case, which is vehicular networks. And majority of us already know the importance of vehicular networks. They're indeed going to help us in the safety features, and we're going to have unmanned vehicles. We need to control them. They need to gather information from the control center, maneuver around, and so on and so forth. So this is pretty much known to all of us, right? So now these applications have thrown new challenges in terms of quality of constraints. For example, what we popularly know as ultra reliable and low latency constraint is one such constraint that is imposed in these networks. So that would in turn ask us to relook at the packet size, amount of processing done at each node and so on and so forth. And then we can't really give up on the traditional metrics such as lower error rates, lower energy consumption, and so on. So ultra reliable and low latency communication is going to be on the top in terms of the new requirements in terms of constraints, right? So how do we really secure these vehicular networks, right? So now, if anybody has done a fundamental course on network security, then we are aware of threats such as threats on privacy, on confidentiality. We know about integrity threats. We also know about threats on availability. So these are usually called as the denial of service attacks, and several variants of them, impersonation threats, replay attacks, and many more, right? So I would say these are fundamental building blocks for any attacker. So for any attacker to breach an existing infrastructure, he or she would have to execute a combination of these fundamental threats in order to maneuver around and hack into the system, right? So as a beginner, I would just need to ensure that some of these threats are taken care of, right? So if I go ahead in this particular mentality, then I can do one straightforward thing is that we can ensure that authentication is taken care in vehicular networks. And how do we do that? So for example, you can ask every vehicle to carry a pre-shared key with the core network, where it is connected to the RSU, which is the roadside unit in the backhaul network. And then like how our 4G network or 5G network mobile phones authenticate with the base station, we could have a similar authentication mechanism in the vehicle network as well. So this is going to take care of basic authentication and then secure the channel for subsequent conversations. Now, this is one step that is fairly straightforward. What else can be done? In the context of vehicular networks, we may also have to look at secure neighbor discovery. And this is especially important because vehicles may have to talk to each other, because a vehicle talking to RSU alone may not be feasible because of low latency constraint. And then most of the time, some of the measurements may have to come from the neighboring nodes. So in such a case, we need to think of how to have an authentication mechanism between the neighboring vehicles. How does one vehicle trust another one? And how is the authentication done? How do they communicate after that? And so on and so forth, right? So these are two simple steps that we can go in this direction. Now, suppose once we build such a secure system, so let's say we come up with this picture, wherein you're going to have a big picture of, you have a given area, and then there are going to be a number of vehicles, and each vehicle has a pre-shared key with it, as shown in this particular picture. And then imagine there are gateway units which are around a given area, and then every vehicle that enters this particular area has to first authenticate with the gateway unit, and gateway unit is connected to the backhaul core network, and that's how authentication is done, and then the neighbor discovery is done, and then maybe subsequently that's how it's secure, right? So with this picture, the question that we are going to ask is, are we good? I mean, is it sufficient, right? So anybody who does security will know that there is nothing called as a perfect security. All that we have in security is we need to envisage a set of threat models that we think are reasonable and could be implemented by the attacker. And then against those threat models, we need to come up with countermeasures that are proven to be secure against those threat models. So if we freeze those set of countermeasures against those threat models, and if we are reasonably convinced with their architecture and implementation, then only we can say we are good, right? Again, conditional on the threat models as well as the countermeasures that we have, right? So we are not good at this point in time, and that essentially leads to the motivation of this particular talk. I'm going to say why we are not good at this point in time, right? So to give you some more details on this, here is an outline of this talk for the rest of 40 minutes or so. First, I'm going to give a background on provenance. I'm going to introduce you to what is provenance, why is provenance required, and what is its role in the context of vehicular networks, right? So this is mostly going to be some sort of a motivation and problem statement setting in this particular talk. And subsequently, I'm going to share a few contributions that have come from our lab at IIT Delhi. And that's going to be the second bullet here, which is low latency provenance recovery methods. These are some of the strategies that we have proposed in order to answer the questions that will be posed in the first bullet. So I'm going to talk about it in detail. And then there is a third bullet, which is a variant of the solutions that we have in some advanced settings. Essentially, the second bullet and the third bullet capture the overall contributions for this particular talk. And then, as usual, like any other talk, we'll conclude this with some interesting directions of future research, and then what we think from bird's eye viewpoint, right, about this entire topic. Okay, so what is the motivation for provenance? Now, multi-hop communication is one such scenarios where provenance is applicable, right? So if, let's say, for the course of discussion, we are going to have this roadside unit, which is like a destination or a control center which gathers the data, right? So if a vehicle talks to the roadside unit directly, then there's a one-hop communication, right? So then, because of prior authentication, the roadside unit can figure out where the data is coming from and so on, right? However, multi-hop communication, where things have already been well studied, we all know that multi-hop communication is going to be very helpful whenever there is issues with coverage, whenever there are power limitations, and so on, right? And then multi-hop communication has been very well studied so far under the topics of end-to-end reliability and end-to-end delay and so on, right? So when multi-hop communication is put on, let's say, the vehicular network framework, right? Then a vehicle is going to talk to another vehicle, and then subsequently these vehicles are going to forward the data, and then finally it reaches the roadside unit for whatever physical constraints that they have, right? So for these applications, whenever the roadside unit receives a packet from one of the vehicles, let's say, which was beyond one hop, right? Then it cannot really verify anything about its identity, right? Because the nearest vehicle is the penultimate node in this particular context. So all that the RSU knows is about the penultimate node, and it cannot really say anything much about the preceding nodes in the upstream of the entire packet flow. So therefore, in such scenarios, the RSU, whenever it receives the packet from these vehicles in a multi-hop fashion, it would like to open the packet and verify the authenticity of the packet from various aspects. Okay, it would like to know where was the origin of the packet from, what was the identity of the vehicle that sent the packet, who forwarded the packet, what are the various processes that modified the packet, and so on and so forth. Essentially, it's like a history, it's like a log. That is something that's clear from the title of this particular talk. It would like to know a lot of information about the packet during its journey, which it could not witness directly, right? And that's the motivation for provenance in vehicular networks. And essentially, provenance refers to the information related to the origin and who forwarded the packet and so on and so forth. Okay, and these are important from a security standpoint, because we know that, especially in the context of vehicular networks, if some adversary gets into one of these positions and then executes an integrity threat or any of these, it could lead to catastrophic consequences, especially when we have unmanned vehicles or driverless vehicles taking care of controls and so on, right? So on a packet-to-packet basis, the roadside unit would like to check the authenticity, and this has to happen with the help of some information from the packet. That's the motivation for provenance in vehicular networks. So formally, we say that provenance refers to the information on the origin of the data, the processes that have modified the data, and various nodes that have forwarded data. This is too loose a definition. In fact, we don't have to really stick to this. It could involve more than what it is. It could involve less than that. Essentially, it depends on what is the threat or what kind of features are we looking at in the packet, okay, or from the packet, in the packet to the RSU, right? So again, to give you a big picture, we already have some sort of a secure wireless network or vehicular network. They already have a pre-shared key. What they need to do is, in order to help the RSU learn about the origin and all the nodes, all of them need to embed some signature in the packet. So they're not going to just forward the packet in a, let's say, an amplify and forward fashion, right? Or even if they decode and do some processing, they are not just going to forward it as it is. The RSU or the roadside unit will ask them to embed something into the packet so that it can figure out possibly detect threats or figure out the authenticity of the messages and so on and so forth. So it's some kind of a binding from the legitimate parties as well to accept this particular suggestion and then modify the packet when it is along its journey to the RSU, right? So now what it means is in a multi-hop fashion, when a packet reaches a particular node, the node has to process. So it's going to add some, it's going to incur some delay. And this processing is imperative because the security or the untrusted environment is asking these nodes to embed something into the packet, right? And this is sort of a trade-off that's going to have to be dealt with whenever we address this. All right. So now this type of a provenance, which has to be has two parts. It has to be, this information has to be embedded by the individual nodes when they get the packet. And then finally, the RSU has to recover this information when it receives the packet, right? And then this entire framework of provenance is not new. So I have listed a few good articles that we have come across. In fact, provenance and its recovery methods are very well known in the context of storage networks. However, with the wireless network in mind relative to this particular talk, when sensor networks was in boom a couple of or a decade back, there are a number of contributions related to how to embed the provenance data in a packet, how to recover it, and so on and so forth. And then usually what we do is we classify provenance recovery methods into two parts. The first one, I'm going to call it as non-adversarial because these are mostly not against any threat model. These are used to probably, study in diagnostics point of view, figure out how many nodes are alive, especially given that, wireless sensor networks then used to be, so were battery energy constrained device and so on, right? So there have been a good number of works on ensuring, how to embed provenance. Given that they're embedding provenance, then that takes up additional time and space, right? So then how to reduce the additional communication overhead and so on and so forth. I see a raised hand. I can stop if you want.
Yeah, if you don't mind, had a question regarding the provenance detection. Is there a specific reason why you want to do it at a per hop basis instead of doing at only at the endpoint, that is the receiver? And second is, again, like why do it on a per packet basis when you could do that on a per message basis? And because anyways, the protocols, higher layer protocols have some form of checksum or integrated detection at the message level itself.
Yeah, it's a good point. To answer the first one, the threats could happen at any link in the network. So so it could be a jamming attack in one of the hops, and then that adding information related to that would be meaningful at that particular hop. So threats can happen in any granularity at that level. Per hop is required. And to answer the second point, I agree that once a list of packets are accumulated, then probably you could run a CRC check or probably do a message authentication code or whatever it is. Now, in the context of low latency communication, this is actually an impediment because when there is a deadline for messages to reach the destination, right? So if we wait for verification from the CRC level at the higher layers, then we believe that a lot of time is lost already, right? So as far as possible, if we can detect threats at a much lower level, right? And then if you can save that much amount of time and then take appropriate decisions, then you would actually buy more time. And eventually, if countermeasures are implemented, then by the time the packet reaches successfully, then maybe the latency constraint is met. So latency constraint is one of the key reasons for that.
But this precludes the possibility of the nodes or the lower layers of reorganizing the packets, especially since the wireless protocols are involved. Like some like MAC protocols require the messages to be split, and then this will cause the provenance detection break, right?
So provenance, so it's again the granularity at which we are looking at. So if I have to verify the authenticity of every packet at that level, right? So then I will have to dedicate a few bits to carry this metadata, and we can take a look at it from a per packet basis. So they will have to do it.
Oh, okay, thank you.
Does that answer your question?
Yes, yes.
Okay, thank you. So I'll proceed if there are no more questions. So as I was saying, diagnostics point of view was one of the approaches wherein people have looked at how to compress that information, because this is always a communication overhead, right? So people have looked at compressive sensing based techniques, arithmetic coding techniques, and so on. So essentially, they have all been to reduce the communication overhead and yet deliver what they are supposed to deliver to the destination in that language. Now, there is one more class of research contributions which have looked at adversarial environments, wherein they take a look at, or they consider a few threat models. For example, this could be a packet dropping attack from some of the nodes, or let's say forgery attacks and so on. So then what they do is they design their embedding algorithm in such a way that these attacks get detected at the destination or the control center when the packets are received, right? So the idea of embedding metadata into the packet is the same, but their design is for a different reason. In some cases, they are just to provide diagnostic information, which is the former one. And in the latter one, we have specific designs wherein they are designed to detect some of the threats, and then the subsequent analysis is to whether their strategies are able to detect with high probability or false alarms and so on, misdetections and so on. So that's the high level bifurcation. And these things are already known in the context of wireless sensor networks. So provenance as such is not a new topic. Then what is the problem here? So since we are talking about vehicular networks, now vehicular networks, as I mentioned, this is already part of one of the answers in the previous slide. They ask for stringent delay requirements, limited delay, and the requirements are new compared to classical wireless sensor networks. Now, when a vehicle has to open the packet, has to modify the provenance portion of it, then it's going to incur some delay. And this particular additional delay may not be suitable to the latency constraints asked by the RSU, right? So therefore, is there a new problem that we are facing in terms of vehicular networks? Is what one of the first questions that we had. Although there are provenance methods available for wireless sensor networks in the past, can we really reuse it, or are there new questions that we can pose in the context of vehicular networks? That was one of the questions to start off this particular work as part of motivation, right? So what's the simplest thing that we can do? If we want to find out the nodes that have modified the packet or have forwarded the packet, we can actually ask each of these guys, raise their hand or probably sign their identity saying that I'm the one who sent it, I'm the one who sent it in the packet, and then the metadata will be filled with these identities, and then the RSU can figure out that, right? So now this is one straightforward way of doing it, right? But then if you are asking for the nodes to only embed their identity, then there are certain situations where that is not helpful any longer. Okay? So for example, in the multi-hop network setting, the RSU may want to apply some distance bounding algorithms, right? So in order to measure the distance through the packet delays and so on. In such cases, even if, let's say, one of the nodes executes a denial of service attack, let's say by skipping his signature, then what happens is the RSU would think that, the number of contributors is less than what they were supposed to. And then this would in turn lead to inaccuracies in the estimated distance bounding, right? So now the point, it goes back to the same thing, saying that if we have a threat model, then depending on that threat model, we would need to design the provenance methods, or let's say design how to ask or what to ask the nodes to embed in the packet. Right? And then there are other applications. For example, if you are looking at crowdsourced inference mechanisms where, a vehicle may have to pass on some information related to what it sees around itself, right? For autonomous vehicle movements. And then, every vehicle may add some information from its perspective. And then eventually the packet will have information from several nodes, several vehicles, and then the RSU might have to make an inference based on all the parts of the message, right? In such a scenario as well, if we have an adversarial node that attempts to execute an integrity threat or manipulate the contents of some other vehicle in the same packet, then it's not easy to detect this, right? So in such a case, if you're asking for the individual nodes to sign their identity, that may not really be useful. So we need something more. For example, we may want to know the order of the nodes that embed the provenance. And why is the order required? The order is basically who started it, who gave it to whom, and so on. And why is it required? It's required because to check any integrity threat, right? So then we would need hash chains, right? So there is hashed message authentication codes. And then if you want to verify the hash chains, then you would need the right order. Otherwise, your complexity would blow up to factorial h, where h is the number of hops, right? So this is one such instantiation where you can define your own definition, your own provenance. So here I'm going to say that provenance is not just about the identity of the nodes that send the data, but I'm going to add on to say that provenance is the order in which they send the data, right? This is another definition. So depending on the threat that that is potentially there in the network, tomorrow we may come up with another definition of provenance where it may include a lot more data about many other things, right? So this is just an example to say that the definition of provenance depends on a threat model, right? So now let's just take a look at this new definition of provenance where I'm interested in learning the order of the nodes along with their identities, right? And then once we are looking at the vehicular network concept, they come with new constraints which are possibly not there in the context of wireless sensor networks. And what are these? And these set of constraints make the problem new, and that's why we were a bit excited about this. And what are they? And one of them is number one, the RSU may or may not know the topology. What do I mean by topology? Topology is basically the configuration with which these vehicles are spread across a given area, right? So it may be possible that one vehicle can talk to other, possibly because it's in a nearer range, but then it may not be able to talk to another vehicle that's far away, right? So in which case you are sort of building a graph. And then you're saying that a vehicle is connected to another through an edge, and then you have a network of different topologies. Now, this topology information may or may not be known. Why? Because of mobility, right? So these vehicles could be moving around, and at one instant the configuration could be something, at a different instant could be something else. So how do we learn the order of the nodes through which the packet came in the provenance under this particular constraint? Number two, low latency that I already mentioned. And number 3 and 4, these are standard in the sense, whether it is wireless sensor networks or whether it is vehicular networks, I would want to reduce the communication overhead, that additional space taken by the metadata. And finally, I would also want the network to be scalable, or rather the strategies to be scalable in the sense that, I should be able to detect the provenance accurately with arbitrary number of vehicles in this particular network, right? So that brings to the end of the motivation of provenance. What is provenance is done, and why provenance, or how is the problem statement for learning provenance is different in the context of vehicular networks. So I can take a break and take a few questions if you have on the motivation, so that, if we are through with this, then probably we can move on to the other parts. Shall I proceed?
Please go ahead.
Okay, great. So, now that the problem statement is clear, I'm going to talk a bit about some of our recent contributions in this space on how exactly to design strategies to help in provenance recovery at the RSU. So remember, there are two portions to it. Number one is the participating vehicles need to embed this information in the packet. It's number one. It's called as the embedding process. And number two is once the packet is received at the RSU, that would need to recover this information somehow through this metadata. So it constitutes two parts, right? Now, one of the main tool that we have used to embed provenance is what are called as Bloom filters. And these are classical, very well known probabilistic data structures that are used to embed the membership of any element, and then they're also useful for verifying the membership of any element in a given set in a constant amount of time. Right? So the idea is fairly simple. You're going to have a set of bits allocated for provenance. So that's what I call by metadata. And the size of this particular, the number of bits is fixed, right? And then this is a common space for everybody to modify in the packet, right? So we don't really want the packet to grow as the number of hops increases. Therefore, we have to judiciously find an appropriate value of this size. And once this is fixed, what happens is a vehicle has its own identity. It has a unique identity, and using which, it's going to, in a pseudo-random fashion, is going to choose some k locations in this particular space, and then it's going to set it, right? And then likewise, another vehicle that wants to modify the provenance or want to embed its information, it's going to use its ID and then embed or set some locations. Now, the characteristics of Bloom filter is that, or the simplest Bloom filter, there are many variants to it as well. However, the simplest Bloom filter is such that you're going to have zeros to start off with, and then anybody who wants to set some of the positions is just going to make a 0 to 1, and then if the 1 already exists, then 1 is going to be 1. All right, and then this is how they're going to embed and then forward the packet to the next node. So likewise, this is going to happen, and then ultimately the RSU is going to receive this particular portion in the packet. So I have not denoted any other portion; it's only the Bloom filter portion. Now, one of the problems, although the embedding methodology is fairly straightforward, one of the issues with Bloom filters is that it has high false positive events. What I mean by that is, let's take a look at this particular example. Now, this particular vehicle has chosen these 3 locations. This was in pseudo-random fashion, and then this vehicle chooses the other 3 positions. And then, as you look at it, the vehicle, the positions chosen by the third vehicle already coincides with the positions taken by the other 2. Now, what happens is when the RSU is going to look at this particular packet, even though the third vehicle might not have participated, despite that, it will give an impression to the RSU that the third vehicle has also participated. And this is essentially what is called as the false positive event, which is a node has not participated in the embedding process, however, has still been recovered due to the properties of Bloom filters. Despite this limitation, Bloom filter is still popular, and then it's attractive because of simplicity or because of low complexity operations involved. And if you are wondering what is the source of these pseudo-random positions, the IDs are known to the RSU as well, because these IDs, you can think of them as getting derived using the pre-shared keys, and then they could use these IDs and put it into a hash function, and the hash function could generate these locations. And likewise, the RSU, once it receives the packet, it has the identities of all the nodes with it. Okay, and then what it does, it can just do one by one. It can verify the membership of each of these nodes, and then identify which one of them has contributed and which one have not. So that's basically the background on Bloom filters. So I need to use this in order to explain the methodologies that come later. Right? So as far as the packet is concerned, how does the packet look? It's a typical packet as whatever it is. You're going to have header, payload, and so on. But then now that we are going to propose Bloom filters in it, Bloom filter occupies a set of embeds somewhere in the packet, a form of the metadata. And this packet may or may not have other features. You could have a MAC, which is the message indication code, possibly to detect integrity threats. You could also have a hash chain potentially. And these are optional, but for the time being, let's just look at the presence of Bloom filters in the packet structure. We would need these in order to carry forward and then talk about our ideas. Okay. So what's the idea? One of the problem statements that we discussed so far was that the RSU must recover the order of the nodes and not just the identity of the nodes that forward the packet, right? So the order is important, right? And then given that it's fluid, and, there's mobility in the vehicle network setting, this somehow has to be preserved. So how do we achieve this using Bloom filter? The idea is fairly simple. Before the payload is sent, you just have to recall that the neighbor discovery phase was done, meaning every node knew their neighboring nodes in terms of formal authentication, right? So what they could do is when a node receives a particular packet, for example, if packet is received by this particular node, instead of embedding the information on its identity, okay, it's going to embed information on the edge, okay. So it's not the node information, it's the edge information, right? So against this particular unique edge, it's going to set the Bloom filter appropriately and send the packet to the next node. Likewise, the next node is going to embed the information on the preceding edge and then update the Bloom filter and so on and so forth, right? So nothing new. All the Bloom filter characteristics have been taken care. It's just that the attribute that is used to embed the Bloom filter is edges, set of edges, and not the set of nodes, right? And then what happens at the RSU side? RSU has a list of edges of the entire network, and then it's going to verify the membership of each one of them in the Bloom filter, and then it's going to gather a set of edges, right? So that's the broad level idea, and these are just the details into how these ideas can be implemented. Essentially, as I mentioned, we would need to come up with a unique identity to the edges, and then that should be fed into the hash function, and then the hash function chooses the appropriate index in the Bloom filter. Right. So likewise, at the receiver, at the RSU doesn't know who are the contributors to the packet. So it has to sort of have a set of all possible edges with it, and then it needs to verify the membership of each one of them. And once it verifies is in the Bloom filter, it's going to get a subgraph because of the false positive nature. Some of the edges that were not available or were not present in the path may also pop up. Right? And that leads to a subgraph, and then from that subgraph, the RSU had to figure out the right path, and that's a last hop, the last mile step that it needs to perform. Right? So just to explain that particular portion, here is an instantiation that you see in this particular picture. Now, suppose let's say path 1 is the one that is traveled by the packet. Now, because of the false positive events, right? So then, suppose let's say the Bloom filter size is large. Right, and then then what happens is the collision probability is significantly small, and therefore very highly likely you're going to only recover the true path. And this is possible because there are no false negatives. But suppose the Bloom filter size gets shorter, then the congestion increases, and then the collision probability increases, and therefore, addition to path 1, some other edges may also pop up. For example, this particular edge that you see was not involved in the packet, but still this got lit in the Bloom filter. And for example, this one got lit, this one got lit, and so on. Now the trouble is that this is fine because I can somehow isolate this because this doesn't really make sense to me in terms of path. But as you look at it, the path 2 and path 1, there is a conflict, right? So this conflict has to be resolved. Otherwise, the RSU wouldn't be able to figure out which was the right path that was chosen by the packet, right? And therefore, the false positive event, the nature of events is slightly different in the context of edge embedding. I'm okay to have some false edges lying here and there around the network for my subgraph. But then as long as it doesn't hurt me in forming a separate path of the same hop length, then I'm going to be in trouble. So I somehow need to figure out what is the size of the Bloom filter in such a way that the false positive events, or the rate at which it happens, is minimized. And then how do I do that? Then this is going to give us rise to an optimization problem. Before that, we would need to formulate how does that expression for false positive look like, and assuming a complete graph structure and assuming that the hash functions are ideal, then we can put forth the IID distribution function on the choice of those indexes. And then subsequently, we can look at collision probabilities, and then with a bit of a detailed math, we can, what we can do is instead of obtaining an exact expression for the false positives, we can actually, it is ideally, this is the problem, right? So if I were to have the exact expression for false positives, then my question would be that, how many hash functions, how many index positions should I choose in the Bloom filter? The M here denotes the size of the Bloom filter, and then I'm supposed to choose the best value of the K, which is the number of hash functions, which minimizes my false positive events or the false positive rates, right? So K is the number of ones that each vehicle embeds based on their attributes. Now, if I had this expression, I would have solved it, but then we could not really get this. So what we have done is we have come up with an upper bound using some analytical expressions, and just to give you a sketch of the proof, essentially what we have done is we have tried to identify those events that are false positive events in some sense, because those edges appear. For example, 1, 2, 3, 4, 5 is the legitimate node, the actual path traveled by the packet, whereas the other ones that you see in the dotted line or dashed line, these are the ones that are lying around in isolated fashion, right? So this is one such favorable event where it doesn't cause me trouble, right? So essentially we take a look at all possible structured edges that are not going to cause parallel paths or additional paths of same hop length, and then we are going to quantify the probability with which these events occur, right? And then as much as possible you accumulate these in a structured way, and then this in turn would give us some bounds because we are not capturing all possible such events. So I'm not going to get into the details, but that's the crux of the proof and how it is done. And then once this is taken care, then we have an expression. What is that? It's going to be an upper bound on the false positive. And as you can see in this particular plot, this particular upper bound that you see in orange is not tight when the Bloom filter size is low. But however, the good news is that when the Bloom filter size is large, for example, the bottom plot that you see, the minima with which the experienced by the orange plot is very close to the minima that is experienced by the blue one. The blue one is the true one, right? So the consolation is that at least now I have some analytical expression with me using which I can compute the best value of k, although it's an integer single dimension optimization problem, but still this could be done, and then I can fix a particular value of k and then use it and ask all these nodes to use the particular value of k to implement the particular strategy, right? So that's the solution. So, you can think of generalizing this in multiple dimensions, right? So one such is to go from edge to hyperedge, right? So a specific example of hyperedge here is a double edge, what we call in sense. So for example, if a particular node knows where the packet is coming from and where the packet is headed to, then it can embed not just the edge ID, it can embed the hyperedge ID, which is a double edge ID. So it can associate an ID to a double edge, which is a pair in this case, and then this can be fed into the hash function, and then that could potentially choose a set of locations in the Bloom filter, and then forward the packet. So the benefit of doing double edge embedding is that, as you can see, only alternate nodes need to embed, and this, given that we also have low latency constraints in vehicular networks, we have seen that these ideas help, because you're asking at most half the nodes in the path length to skip marking, and those who skip are essentially taking care of the contributions from their neighbors as well, right? And then this is pretty much the same. It's just that we have generalized the idea of embedding the edge to the hyperedge of a double edge, and the rest of the process is the same. The problem statement is still the same, which is I would need to still compute the number of hash functions, and the solution is also similar. We have come up with upper bounds on come up with analytical expressions on the error rates. The proofs are similar. However, the nature of events are more involved due to the presence of double edges. And likewise, we have also observed that the bounds are not so are still useful, because in certain regimes, we can still obtain the value of number of hash functions k, and then still use it in the context of the true expressions because they are very close. Okay, so that's the analytical part of these ideas, which meant we had to solve these math and then figure out the best values of k. And I'm going to take a bit of time for the rest of the 15 minutes to talk a bit about how we have evaluated or rather validated these ideas on a test bed. So we have made use of what are called as DG-ZigBee devices. So essentially these are variants of ZigBee networks. They work on the ISM band, and these are not so expensive. They're available in the market, and you can't, unlike an RSC, unlike a software-defined radio, we can't manipulate the physical layer characteristics of it, like modulation and so on. But that's frozen. That part is frozen. But it allows you to access the packet structure, and then there you could divide the packet structure into payload and Bloom filter and provenance and so on. So essentially, that was taken care by the ZigBee devices. And the computing counterparts for the ZigBee devices were Raspberry Pis. And then we were able to demonstrate several things, including the error rates, false positives, and importantly, the low latency aspects of these ideas, because essentially we were targeting the vehicular networks for this particular use case. Right? So a bit of a background on ZigBee devices, XBee devices, and there are Python interfaces to this. There are a lot of state-of-art information is available on this, very easy to manipulate and work with. And after all the manipulations here, here we have a set of plots in order to showcase what it means to implement this in this particular framework, right? So on the x-axis, we have the provenance size, which is the number of bits allotted for provenance from in the packet. So this is where every node is going to embed some information, right? On the y-axis on the left, we have latency. On the y-axis on the right, we have the error rate. Error rate is basically the confusion with which the RSU won't be able to resolve. And the takeaway points here, first in terms of latency, is that as you can see, the black one corresponds to the hyperedge. It's a double edge one, which is essentially the nodes. Some of the nodes skip in between, right? So they facilitate skipping, in turn reduces the delay. And as you can see here, we can actually gain a few milliseconds here. And that's the advantage in terms of implementing double edge. And overall, because hash functions are rather quick implementation, right? So in general, both edge embedding or double edge embedding are feasible for low latency application. It's just that, between the two, double edge does better. And also in terms of the error rate, we also see that double edge does better. Now, that was a bit of a counterintuitive result in the beginning, because when you look at all possible double edges for verification, that grows polynomial of degree 3 in terms of the number of IDs to verify. Whereas the number of edges is still quadratic. So we initially thought that, for a given Bloom filter size, double edge is more dense. But in contrast, what happened was that the granularity with which you're looking at for double edge is, it's a pair of edges that lets you throw away a lot of false positive events. And as a result, we saw that double edges do outperform in terms of false positive events, right? So there are some more variants to some more plots for several parameters. And I don't want to get into the details, but I would want to maybe take 5 more minutes on explaining a few ideas about the advanced settings. And this is something that is very recent from our lab. I'll just give you a sneak peek into the problem statements and not go into the details, right? So what is that? Now, whatever you saw before this, right? So there's a situation where the nodes are mobile, and then the topology could be anything. So when we don't know the topology, or when the RSU doesn't know the topology, some sort of a worst case is to assume a complete graph on the underlying topology, and then it can verify all possible edges. And that's the reason it grows quadratic and then polynomial of degree 3 in the case of hyperedges. But then if we have topology knowledge at the RSU through some source, right? Then essentially what happens is you're going to potentially have a sparse graph, possibly, right? And then which means the number of edges that you're supposed to verify is also far fewer than what is there in the complete graph. And that gives us rise to new questions, as in, you ask the same question in terms of figuring out the number of hash functions, but it's just that you have along with all the other parameters, you are also given the topology, or you have a graph underlying. And for that particular graph, what should be my choice of number of hash functions? So this is an important variant, because this is known to also do better in terms of the error rate, because some sort of a side information is already available about the network, and that's what the intuition is about, right? And another problem statement, which is equally interesting, is an observation here that anybody who has worked with Bloom filter will quickly identify that, especially the primitive ones, right? So they are not scalable. The reason is if you have a fixed set of embeds, and then if you are asking for a lot of nodes to embed in a particular size, then false positives are high, because there is a possibility of high collision rate, right? So we had to think of a way to potentially scale it in terms of the number of nodes. So one possibility is not to cut down the growth rate in terms of the Bloom filter size, is to slower the rate of the growth. So what we can do is along with the Bloom filters that are there in the packet in terms of as part of the metadata, we can also have a hash chain of all the Bloom filter values. So when you have a hash chain that, for example, if you use a 256 bits hash chain, right, then it essentially captures the order in which these nodes have also embedded their Bloom filters. Now, in such a case, what happens is you are cutting down on the growth of Bloom filter, because even if the number of nodes increases, what happens is you don't have to increase the Bloom filter size. There are going to be a lot of false positives. The RSU is going to find a lot of parallel paths of the same hop length. But because there's a hash chain, what the RSU can do is it can apply the same Bloom filter contents and then verify the hash chain using the additional portion. And then 256 hash chain bits is sufficiently large, and then if the collision rate of the hash chain is sufficiently also small, then with very high probability you're going to get the right path, right? So what are we doing here? So essentially we are trying to transfer the communication overhead complexity into the communication overhead into a complexity overhead at the RSU, because you don't want to grow the Bloom filter. Instead, you're asking the RSU that, hey, look, why don't you apply hash chain and verify and resolve your paths, right? So larger the number of paths that it can verify, higher is the complexity requirement. But the good news is that probably my Bloom filter size need not have to grow at a much larger rate, right? So that's the sort of a trade-off, and which gives us to a formal question on, I'm going to say that I have m number of bits for Bloom filter, and then I'm going to come up with a new parameter called beta, where beta is you're going to capture the complexity at the RSU. So beta is going to say, let's say if, the RSU can verify beta number of paths, right? But then beyond this, it cannot, because that would exceed its complexity bounds, right? So if you are given beta number of verification allowed at the RSU and a Bloom filter size of m bits, how do we solve the same problem, which is how do you come up with an actual or the perfect number of hash functions which are optimized for the value beta as well as the Bloom filter size, right? So the same, as I said, it's a variant of the earlier problem, and we could come up with some bounds on this, and then these bounds could be used to understand the intricacies here, right? So I just have a couple of minutes left, and here is just a set of plots to show that you have a scenario where when you have the topology knowledge, the error rates are going to be lower. That's what's captured here in the orange, because you're basically taking the side information and then not verifying a number of non-existing edges, right? So that's intuitive that it does better. And at the bottom ones, you have a set of figures where, again, intuitive, what it says is if your beta, which is your complexity that is allowed at your side at the RSU to verify the hash chains is larger, then you will also do better because you're able to resolve among the multiple paths, right? So that's also intuitive. And then we have shown similar results in the case of double edge as well as single edge. And we have also tried to understand the scaling of it. But one of the catches is that if you want to scale it, then you need more number of devices with your XBee devices. So we took an alternate path to implement the same thing on Omnet++, wherein we could actually grow the number of nodes arbitrarily and then also study the same thing. The metrics are the same. It's just that in one case we were measuring the latency and other things on XBee devices, whereas in the other we were doing it using the Omnet++ platform, right? So that's the, in essence, what has been done in the context of low latency provenance recovery, right? So Bloom filters are favorable. They have an advantage because they are easy to implement, and that's potentially why we say that it's appealing for low latency. But then they also come up with other drawbacks like false positive events. So this is something that we need to be careful when deploying this, right? So last slide. Takeaways from this particular talk. At a very big level, vehicular network applications throw new security challenges. Indeed. So there is definitely a need to revisit provenance recovery methods because of new constraints. This stands at a point where you cannot really take existing methods from wireless sensor networks, right? So there is scope for designing new methods here, right? And what we have done is we have taken a step in this direction by defining a provenance, coming up with a definition where we say that it's the order of the nodes and it's not just the IDs of the nodes, right? So overall, going forward, logging is what we do in the packet. It's imperative, it's important, but we understand that it introduces trade-offs between security features and latency constraints, right? So you want to be secure against many threat models, you want to log more, but you're also spending a lot of time, right? So we need to work with this trade-off. And then what to log and how much to log is something that depends on threat model. And this is something that going to be interesting when we want to carry this for translation to deployment. Okay, so I think that's it. If there are any questions, I'll be very happy to answer. And I think I have 56 minutes.
Hello, Dr. Harshan. Am I audible?
Yeah, you're audible.
Okay, thank you for the talk. Just one quick question. You may have mentioned this before, but what was the motivation for considering the order of the order in the path? Can you just mention that again?
Yeah, so we had two motivations. Number one is on denial of service attacks. So if you ask only the nodes to embed their IDs, then if one of them skips embedding his or her signature, then the total number of hops as understood by the RSU will change, right? So this may lead to incorrect inferences on bounding the distance of a particular vehicle. So in contrast, if we ask them to embed edges, then even if somebody skips, right, then in the provenance recovery, a path is not formed because there are no false negatives. There won't be any path, and this would at least hint or give an indication to the RSU that something is wrong, some sort of a detection, anomaly detection. That's one of the first reasons. Number two is if we know the order, then when we are checking for integrity threats, especially using hash chains, right, we can actually do it in one shot because we know the order. We can keep applying the hash in the same order and then verify integrity threat. If we don't know the order, then computationally it's going to take factorial H attempts, and that would be too long.
Okay. So the order of the nodes actually helps determine the edges, and that's the first point that you're making. Is that so?
Yes, that's right. Yeah.
Okay.
Essentially, they're motivated by the threat, and yeah, that's the answer.
Okay, thank you.
Thank you.
So Harshan, I had another question.
Yeah.
So when you're deriving this lower bound, of course, you went very quickly over it, so I didn't understand. What is the intuition when you try to find this, a probability of having a conflict? This three sides you have.
Yeah, let me just go there and then just go through some of the.
Yeah, maybe just like high level, if you at least you can explain so that I understand what is going on here.
Right. So instead of looking at false positive events, we are going to look at the complementary events where where there is no confusion for the RSU to resolve.
Okay.
And then what I can do is I have to exhaustively list out all possible events in the complementary space, but then it's a challenging task. Therefore, if I can pick up the easy ones, then I have a lower bound on the complementary events, which in turn will give me an upper bound on the true events.
But in some sense, you have to pick the those events which are sort of significant probability events, right? I mean, if you're that's what's going to lower. So, what are those significant probability events in the in the complement which you are picking up?
One such is as you can see here, the dotted ones. The dashed, the dotted ones are the ones where you're concerned. So these are isolated edges. So when this happens, there is no false positive event. So such event. Then here is an event where an edge appears in the Bloom filter, but it is not directed inwards, but directed outwards. Okay. And there are other events where in addition to them, they will not provide a hop length of a given value H, right? And then there are combination of events. For example, there are other events where edges emerge out of a node on the path, and then they hit back on another node before that particular node. So that way, it is one such event where it's not going to conflict as a parallel path. And likewise, this is one more case, and so on. So and a combination of these. So we did try to exhaustively do as much as possible to cover all possible cases, but then after some point it was out of hands, and then sort of a lazy option is to look at only good ones that have a good structure, so that we could apply probability theory and get those numbers.
So, but if you assume some sort of model on the connections, right? Then, I mean, I'm just doing thought experiment. Then you might be able to think that which edges are more likely. I mean, things like that. No, I mean, I'm no expert on these areas. I'm just
no. That's in fact the problem that you see here in this particular slide, the one that I'm showing. So if you have side information in terms of with probability 1, if the RSU thinks that such an edge does not exist, or if it has a topology knowledge, to some, maybe you will have to bifurcate your entire time slot into 2 parts. It's like how you do channel training and then decoding, right? Something like that. First phase you dedicate it for learning the topology, and second phase you dedicate for.
Yeah, but difficulty with that is that if you have mobility, the things will change very quickly, right? So definitely. You have to relearn quite often. Okay, go ahead.
Yeah. So, but the good news is the definition of an edge is only connectivity, and I'm not associating weight to it. So two vehicles could be moving, but as long as they are in their coverage area, the edge persists for a few seconds.
Right.
So that's exactly the point.
Okay. Thanks, Harshan.
Thanks.
Are there any other questions?
Yeah, so I had another question on the Bloom filter. Have you got a chance to look at the ribbon filter that was recently published by Facebook?
No, in fact, well, we have not. Right now, we have been looking at going beyond primitive Bloom filter. So whatever we have done is very primitive. They are known to suffer from very high false positive rates, right? So if somebody works on the topic of Bloom filter, right, exclusively, then their feedback would be that why are you even doing this, right? So, but then we use that as one of the first tools to try out our ideas. But then all the other advanced filters that are in this particular space, we are aware of these. The one that you mentioned, we are not aware of this.
So apparently this ribbon filter, if you have the flexibility of deciding the key sizes, then you can determine the space versus efficiency trade-off in a key size continuum. So you could appropriately determine the key size so that you can keep the collisions within limits or false positives within limits, and also have better space utilization.
Okay, good to know. So here, when you mention key size, I suppose you're referring to the number of hash functions.
I actually don't know exactly the details of that, but probably the number of bits that you consider for running the query.
Right. In fact, there is this framework of adaptive Bloom filters, which are very similar. So what you do is you ask the nodes to be more intelligent, and then you ask them to change the size of the Bloom filter depending on what they think about their collision probability, right? So along the similar lines, and then but on the other hand, you won't have fixed size Bloom filters. You would have it as a variable entity, and who should modify, how much should it expand, and all this. We will take a look at the ones that you have been mentioning.
Thank you.
Any other questions? I suppose the problem statement was clear, and I think if that is clear, I think my job is done.
Are there any other questions? Okay, if there are no more questions, I think we can end today's session here. Thank you again, Dr. Harshan, for delivering such an insightful talk. And we'd like to remind the audience again to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. I have already pasted the links for these in the chat box. And the link to the recorded video will also be posted on the webpage. Thank you and have a great evening.